Greetings, welcome to another video. For most people, it's just going to be gibberish, and it would have been gibberish for me a short while ago. It's just that I've spent some time in the area, and I've spent some time experimenting in the area. And so between the two of those, so I'll just kind of talk at you for a bit, and hopefully it might be kind of useful to someone. I want to try to stay in, being straightforward and not have this be like, what was it that trader Alan Greenspan, if you understood anything I said, then you weren't listening. He said at one of the end of his Treasury conferences. So hopefully it won't be like that, but so I'll just talk at you for a bit, and then we'll show a little bit of stuff. And I'm psyching myself up now to buy some stuff to try to go further along with this. I guess, even before I get to that, I mean, the other thing that I'm thinking is, my background in education is in medicine, and so I'm thinking I probably will go back to just, reviewing medical articles and developments that I find interesting. The problem that I ran into there is, the most significant development of the past 100 years has been the tremendous morbidity and mortality from the recent inoculation program. And I tried talking in one video about that, just mentioning, blanking on the name, nattokinase, which there are two articles, two studies, test tube studies, showing that it enzymatically dissolves spike protein, and the video got pulled. So, I mean, I guess I'll go back to talking about some stuff in medicine, but, it's sort of like, you're stuck with like, well, do walnuts really treat toenail fungus? People are just dropping like flies. So I'll probably go back to some of that, and you might have to read between the lines. If this one doesn't get pulled, read between the lines, if I'm saying, well, this could be kind of helpful for, some kind of sudden things. Something like that. All right, let's get to the gibberish part. So I'd previously made a really crude bitoroidal transformer, and by that you have your primary here, which you would either put an AC current into or pulse it. I'm pulsing it. And then you have your secondaries here, and there are two magnetic flux paths for the secondaries when you draw a load off and you generate a back EMF. They can flow back into your primary, and if it was an AC current, then you'd have to add more power as you draw power off. But they can also flow along on the outside, and if it flows and hits this other secondary, then that's actually beneficial to that secondary if you draw a load off of that secondary. And this was all covered in the previous 4 videos, especially the introductory one. And what was interesting with this really crude setup is when I put a piece of tape right there, there's no air gap on this E-core, put a piece of tape there, it improved the behavior. There was a little bit less getting out here, but there was also more cycling of the flux on the outside instead of going back to the primary. So what I did is I said, well, if they have, if that piece of tape helped, they have air-gapped E-cores. And so I picked up one of those. And I believe that's a 0.5 millimeter on each side for a 1 millimeter air gap. And later what we'll do is we'll put this on the LCR meter and show how the induction in this coil changes when you complete the circuit, and how the induction in one of your secondaries or both of your secondaries change. And the neat thing when you buy one of these things is you can see on the data sheet, like you can look at this model without an air gap, and it'll give the inductance, and it might have a permeability relative to air of, say, like 1200 or 1500. That's about what these ferrites are, maybe 1600. But then they also give it, like with the 1 millimeter air gap, and it might be like 400 or something. And then they have ones with larger air gaps. And so that's kind of neat. So the idea is, the way Thane Hines has been doing this, and I've been reading also like some of the stuff with Tom Beard, and I think he was also like using magnets, permanent magnets, to adjust how the back EMF was flowing, along with some other differences. So as I said, I've got stuff to buy. But what he was doing, and also in the introductory video, what the engineering student was doing, was saying, taking something like silicon steel, regular transformer steel, with the relative permeability about 200, and that would be where this primary is, and then making the legs out of perm alloy with the relative permeability of like 20,000 or 40,000. What I'm doing is just sort of a cheap and easy man's way to do it, is you just use the air gap to create the permeability difference. And does that work? And it actually does work. And in itself, it sort of brings up an interesting question, which is, like, let's say you just like sawed this off and you had like a 1-inch air gap there. There would be no change between the permeability of your primary like that, or when you put this on, because this piece is gone. So would that mean that all of the flux would now flow to the outside because this is just a dead end cul-de-sac? Or because it's the same material, would some get in there? It looks like it improves as the air gap gets larger, but there's still some deformation of your LC. There's still some dampening of the LC oscillation. Now, what's the downside to, just having this thing as, like an upside down T with this part gone, and, just a giant air gap? The downside is that when you lose all of that induction on your primary, it becomes more difficult to make a high Q factor oscillation. And by high Q factor, I mean very undamped oscillation. And you want a very undamped oscillation. So you kind of have some competing issues there. And the better way to do it, I'm pretty much convinced, is the way Thane is doing it with different materials. And I finally picked how I'm going to do that. And that's something I'll be working on. But it's also worth looking at this more. And I think I'm going to get another one of these with a slightly larger air gap. And this is 1 millimeter. I'll get one with either 2 or 4. I might get both of them. Now, you can compensate to some degree for the loss of Q factor if you have a larger mass. And it gives you more room to get more wire on. And that allows you to compensate for that. But this is the second biggest one of these they make. And and then after that, it would start getting expensive. And as I said, there's going to be better to just use different materials. But it'll be worth following this a little further along to look at a bigger air gap. And then the other thing I'm looking at is the turns ratio. So I had this thing with this wound all the way out to the edges, and I've just been bringing it down, down, down to see how the turns ratio affects the behavior of the thing. And I think I'm slowly starting to get a handle on that. Ironically, this thing doesn't work any better than the one that wasn't gapped with a piece of tape on it. Works about the same. But I think I may be able to get it to work a little better with this next one that I'll show you when I finish this video. And then again, I want to look at a bit larger one and a bit larger one with different air gaps. And then I want to go to 2 different materials. But let's just look at a few things, and I'll talk at you some more. So right now, I don't have the secondaries hooked up. I just have the primary hooked up. And so the red and these lines are bus lines from your bus lines. They're going into the cap, and so when they switch on, the cap charges, then they switch off. The cap's just sitting there, and then the cap discharges through that black SSR, and it discharges through this primary coil. And so you have an LC tank circuit. And if you measure the inductance here, and you know the capacitance, then you can figure out the resonant frequency. So again, just, for like the umpteenth time to kind of review, when you have an LC tank circuit, when this discharges, let's say it's at 10 volts, it throws all of its current into here. This current reaches a maximal, that goes to 0, and the current starts going down. And because the current's the changing magnetic field is going in the opposite direction, it drives a negative voltage into here. And so this cap starts becoming negative. Then all the amperage has gone out of your coil, and this is sitting at, say -8 or something like that. And then it goes back the other way, puts current in, and then this goes to like 6, and they oscillate back and forth, an LC tank oscillator. If this goes from 10 to -4 to 3 to 2 to 1, then it's very damped. If it goes from 10 to -9, then it's undamped. And another measure of that is Q factor, which there's a formal definition, but I'm just using it as a general term for how damped the oscillation is. What I'm really interested in is how far you can get this thing to go negative from its starting voltage. So first, let's just pulse this thing without the secondaries hooked up. So we're just pulsing a coil. That's all we're doing. And so, here's the code. That's the time that I come up with both from the spreadsheet, which gets you to within a couple percent, and then you fiddle around until you find the exact spot for where it goes most negative. So pin 9 goes high, and we charge the cap for 500 microseconds. I'm actually going to charge it for 2 seconds just so that we can see it when it's charged, and then that shuts off, and then pin 8 goes high for on time, and on time, as I said, turns out to be 340 microseconds, and then that shuts off, and then that's all we're going to do right now. So if we turn the power on, we're at 9.9. I was shooting for 10, and it's going to it kind of, I don't want to get OCD with it. So I haven't like super glued these together or anything, so you want to make sure that these are lined up right. So 10.01, oh come on, I was getting it at least to like -9.1. There we go, like -9.13. So it went from 10 to -9.13, and that's pretty good. That's pretty undamped. Could we make it better or worse? Yes. And what's one simple way of doing that? If I took this 4.7 UF out and put in a 10 UF, it would be a little bit worse. And why is that? That's because the pulse duration is longer. Shorter pulse durations are better. I think it was probably like as boring as this video, but probably one of the best videos I put out was something very early on instantaneous amp flow and in an inductor. And that explained just from the conventional equations why, if I went to a 2.2 instead of a 4.7, then it might go to like -9.25. So why don't I do that? Well, the reason I don't do that is because you can't catch it. This is about as small. Maybe I could catch a 2.2, maybe an 01, but you get to the point where you just can't catch it on the DVM. It just doesn't have time to register. And I can't figure out an easy solution to that. So what I'm saying, I'd love to put in like a 0.1 UF cap. I just can't get a reading, and I don't know a solution to that. You can't just like put in a resistor that doesn't really, I mean, the voltage is lower, but it still needs the same time to try to register something. And if the cap is just draining out through the 10 mega ohm resistor in here faster than it can settle down on a voltage, then you can't read it. And even at this 4.7, you know, it's right at the limit of where you can say, all right, I think I see what it's saying. And 10.02, I think I saw 9.14. So that's why I'm not going any smaller. But if you went smaller, with faster pulse, you'd have an even less damped oscillation, even higher Q factor. So, I mean, just a couple points real quick is, you know, why do you care about the Q factor? That's your inductive spike, okay? If instead of letting that flow back into the cap, you shut the thing down when the amp flow was maximal here, and then just had a backwards diode out to a second cap, all of that would flow to the second cap, except for it would now have a 0.6 volt drop across a rectifying diode. So the better you get that, the better your inductive spike would be, you know, like for sort of a Bedini schoolgirl setup or for a buck boost converter. So with this going from 10 to negative 9.15, then say 0.6 across loss across a diode, this would be about 85% efficient. So you can see the higher you can get that, the better. What are the factors that affect this? So all other things being equal, the Q factor, how damped the circuit is, how negative that number goes, improves as a function of the ratio of the resonant frequency time over the tau time of your coil. So the resonant frequency time is 2 pi times the square root of the inductance and the capacitance. 2 pi is a constant, so let's just get rid of it. So square root of LC, what's the tau time of the coil? The tau time of the coil is L over C, L over R, inductance over resistance. There's some point where I read, I can't remember if it probably wasn't a patent. I don't read much Tesla. I mean, I should. But he was saying, I'm looking at coils of high inductance and low resistance. So it's your resonant frequency time. Now, if it weren't an LC tank circuit, that would just be your pulse time. Resonant frequency time over the tau time of the coil. So square root of LC over L divided by R. You can rearrange that then, since it's over L divided by R would be times R divided by L. So the important ratio is square root of LC times R divided by L. And there's a couple corollaries from there. One is that things improve for capacitance as a function of the square root. So if you go from a 16 farad capacitor to a 4 farad capacitor, then that ratio is halved, which is good. The same thing with inductance. You went, you know, from 16 henries to 4, or from, I'm getting confused, square root of L over L. So if you went from 4 henries to 16 henries, that ratio would be halved. However, it's not a square root relationship with resistance. With resistance, if resistance goes from 4 ohms to 2 ohms, it's halved. So resistance is very important. So that's one interesting corollary there. Another interesting corollary is if the thing is set up as an LC tank circuit, adding wire in and of itself doesn't improve the Q factor. All it does is slow things down. Now, why is that? Because let's suppose that you double the number of winds here. So you've doubled the number of winds. What happens to the inductance? in general, and you know, it depends a bit on the shape and this, that, and the other. Yeah. But in general, when you double the number of wines, the inductance goes up fourfold. So your inductance goes up fourfold, your resistance doubles. Therefore, your tau time has doubled. Now, what happens to your square root of LC? Well, C is still the same. Let's say you're just using a 10 UF cap, and you just keep the same cap. C stays the same. L has gone up fourfold. Square root of 4 is 2. So the time doubled, and this doubled. So in other words, what I'm saying is that if you just add more wire and you keep the same cap, then this tau time will double and the pulse will be twice as long. And so the Q factor will be the same. Now, if you're just pulsing the thing and you kept the pulse at a constant duration, yeah, when you add the wire, it will improve. But that's another sort of interesting corollary there. Now, that ratio holds true. I think I said at the beginning, you know, all other things being equal, but other things have a tendency to come in and kick you in the ass. So what are some of the other things? Well, for one thing, is just like your switches. I like to keep everything opto-isolated because I'm self-taught, and you know, this is complicated enough, and they got opto-isolated solid-state relays. Now, what's the one drawback with them is, like, if you go on the data sheet for this Comus AC37, I think it says this fastest switch it'll do is 200 microseconds, and that's actually not true. You can kind of overclock the thing, and that's because that's when you have a 10 milliamp into here. But the actual, if you don't put a resistor in, it hits it with like 50 milliamps to the LED there. And so this thing will actually switch down to about 50 microseconds. And that's, what is that? Now, 50 microseconds on, 50 microseconds off, that would be 10K. So 10K hertz, which, you know, is not bad, but it's not, you know, it's certainly not radio frequency. So A, you can't go that fast. B, even at 10K hertz, if this was, say, like 6-gauge wire, then you start running into skin effect. Now, what does skin effect do? Skin effect increases your effective resistance. And I just got through talking about how resistance is way, way important here. So you start running into skin effect, you're screwed. So what do? Well, you leave the wire gauge, and you know, you can go on the American wire gauge chart, and what were we saying, 10, 20K hertz, somewhere around there. As long as you're, I would say 18 gauge or larger, I'd have to look it up, then you're not going to run into a problem. But you can't go any bigger than 18 gauge, and you know, saying how resistance is such a big deal here. So could you get around that? Well, yeah, you could. And how would you get around it? Well, you could have a bifilar coil, or you could have Litz wire. You think I'm the only person that's noticed this stuff? You look at those coils that John Bedini had, like on his machines there. I actually bought one, and the effective wire gauge, it's like 0 gauge. I mean, it's like as thick as your finger. He's got like 12 or 15, I would say they're 20 gauge wires all wrapped together. So that's why he was doing that. Now, what's another thing you can run into? The skin effects is really from the one wire being next to the other. That's why there's the skin effect. So the other problem you have is when you stack all these up, you run into the same problem. This one on top of that one on top of that one. Each layer is doing a skin effect problem. So how would you do that? Well, you might go to something like a pancake coil, and you might have like a space between each wind. You ever see that before? I'm not trying to be, but I mean, if you look at Tesla, some of the stuff Tesla had, I mean, he had these pancake coils, and he often had spaces between each wind. So again, that's to get away from that so that you can go faster, and that improves Q factor. Okay. So later, probably this year, I'm really wrapped up with this right now because it's pretty cool. I'm going to 3D print what I'm going to call dunce cap coils. And that's because I try to wind pancake coils and they're a real pain in the neck. And it's just hard to do them. But you can get almost the same thing if you just printed, like 3D printed a scaffolding like a dunce cap, so that basically they're not, there's like one of them's a little bit over the other. But then it would be really easy to wind and it would almost be a pancake coil. So that's something to look at down the line. So to try to get back on topic here, what I'm doing after I read a little bit more was what, it's kind of hard to follow, Tom Bearden. Don't destroy the dipole. Sorry. But I'm pretty sure I'm not doing exactly what he was doing with the mag, and I'm not using an AC transformer, AC input, so it's not exactly what Thane Hines is doing. I'm pulsing it, but I'm leaving it as an LC tank circuit, and I'm trying to take advantage of that. And keep that, like when it swings back up, and whatnot to decrease your amp draw. So let's just do a couple more things, and then I'm going to rewind this once. And I've learned, I think, about as much as I can now from with looking at the different turns ratio. So if we look again, we're just going to keep it at one pulse right now. We're going from 10.02 down to, see, it was like 9.13, wasn't it? And now we're at 9.2, so it's kind of hard to get a good reading. But now let's connect one secondary. Bear with me. Okay, and we'll turn this guy on. And what do we got? Nothing. Okay, we connected one secondary. And you can see it's starting just slightly to dampen out the oscillation. And we have a little bit of voltage. 5.7. So that just stinks. Now let's connect the other line of the other secondary. So 0.7. So now I've connected the other line, and now it's much more, 2.66, and we're getting about that 3.38 out of the other one. But you can see it has greatly dampened the LC oscillation. So that's why I'm saying, like, if the air gap there was like an inch, would that dampen it? Even if you start off, only getting from 10 to -8. But if, now this was like -7.9, you'd still be in a much better place. There's one thing to consider here, though, is that, each time I'm discharging the caps back to 0. So when you have an empty cap, I mean, that's almost the equivalent of shorting the line, until you get some voltage there. So, for instance, if we do 2 pulses, and I'm going to get rid of this delay, then what we see is the LC tank oscillation starts to tend back towards where it started because it's not as loaded. So there is deformation, and that's just basically, this is a very jury-rigged thing, and I think even with a well-built one, there's still going to be a bit of deformation, but not as much as I get with this. So really the most interesting thing, I've gone back to one pulse, is that, oh, I have that hooked up wrong, but whatever, is that when you load one side, it greatly improves the output from the other. So I'm going to disconnect one of the secondaries right now. And you see the dramatic change there. That's really the neat thing about this, is that the portion that doesn't flow back and cause you to have to either, you know, when you're looking at it here, because it would be deforming the thing. If you're looking at it with an AC, you know, input, you'd say it's changing the impedance. And you know, you need to add more current. The back EMF that flows back over here is now not counterproductive, it's synergistic or productive. The two coils are in a symbiotic relationship. That's the word I was looking for. So that's what's really special about this. Thane Hines and Tom Bearden was looking at the stuff, and others have pointed out in comments that others have been looking at the same stuff. What else? There's a couple more things to cover, and then I'm gonna take this back to Santa's workshop and rewind it. We'll see if we can improve the unloaded Q factor a bit. So what's the last point I'd make here is that, you know, I'm trying to capitalize on, you know, as I showed it in the other one, where that goes back then positive to, you know, like 8, and then you only have to charge it from 8 to 10. Where am I now? Okay, so I've disconnected the secondaries. If you put a backwards diode in there and just drew this off now with this thing going to -9, and say, oh, well, I'm going to capture the induction, I'm going to put it in another spike there, and, you know, we'll let this go back to 9 or whatever. When it's at -9, what are you going to see in your other cap there if you run this as a, you know, as a buck boost, kind of the Bedini backwards diode thing off of here? You're going to see 0. You're going to see 0 in the cap. Now, why are you going to see 0? Because you have to think about the LC tank circuit. The cap discharges, goes from 10, it goes to 0. When this thing is at 0, the amp flow is maximal. When this thing has gone to -9, that means all of the amp flow has gone back into here, and there's now 0 amp flow in your coil. So you just have a dead coil there. So if you shut everything down there, when this thing has gone back, then you get nothing. You get nothing with a buck boost. So what do you do with the buck boost? With the buck boost, you cut the thing off when the cap has gone to 0, and your amp flow is maximal. And now you can capture the whole change of the magnetic field. If you wait till there, the magnetic field's already changed. So the drawback there is that you can't try to play shell games with the voltage here, because you have to catch it when the cap's at 0, because that's when this is maximal. So what's interesting is that anything at all shows up here when this thing's at -9. And that's again because all of the back EMF isn't flowing back into here. Now, if you just had it, you know, like a conventional coil where, you know, here's your primary, here's your secondary. You do actually, it didn't behave the way I thought. I thought it was going to be 0, just like with the buck boost. You do get something that shows up, but and this goes a little bit, you know, negative. It's not nearly as good. It kind of stinks. There's probably some interesting things you can do with it, but it's not at all the same. I guess the point I'm trying to make here is that with like a buck boost or something, you wouldn't be getting anything. Now, with the Bitoroidal, if I shut the thing down when the cap is at 0, you get a much more powerful spike off of your secondaries. But, you know, your cap's at 0. Whereas here, you know, you can have it go 10, -9, back up to 8, and you still get something out. And even though it's weaker, much weaker, it's more than made up for because you can play a shell game with what's in here. And that's really what I'm doing. That's a little bit different than what Thane and I think what Tom Bearden were doing. It's all the same shuffling with the magnetic flux, but I'm doing a shell game with the LC voltage. So just to kind of reiterate that, here I'm giving it 100 pulses, and you know, we're going where the cap's going most negative, and we're still not even back to 10 volts. Now, if I take it out to 1,000, then we should see that it does transform voltage higher than your starting voltage. But what are we looking at there? Like 16. I'll tell you what. Let's drop this in half. 345, 172. And now, yeah, see, much better transformation of voltage, but now you can't play shell games with that. So you can see why I was interested in the turns ratio to try to improve the transformation of voltage, and I improved it a little bit. But really, the way you want to use this setup this way is, you know, like have 18 volts going in, say 2 9-volt batteries, and then one 9-volt battery, one 9-volt battery. It's doing better, you know, at lower voltages there, because it doesn't transform voltage well, so far. So the last thing I'm going to do is I'm going to rewind this and see if we can't improve the unloaded Q factor a little bit more, and then we'll wrap the video up. Okay, so to try to draw this to a close, so I had some 22 gauge on there previously. I don't know what this is. It was just lying around. This is all I had. I was hoping I would fill it out entirely, but it doesn't. It feels a little thicker. I don't think it's 18. I think that's 20 gauge wire would be my guess. Now what I can show you here, so it's 0.804 millihenries, and then we put the other part on it, and 2.76. So a little bit more than threefold increase. Well, let's get that. So yeah, 0.84 to 2.7. So a little more than threefold increase, and that's because you're completing the magnetic path across that little air gap. Now, if we look at one of the secondaries, it's 1.81 millihenries and complete the magnetic path, and 18, right around there. So the very last thing, I said I thought that this might be a little bit higher Q factor, and it might not work. It might not be noticeable. And just to, you know, mention one more thing, you know, that, you know, all things being equal, the resistance across the switch there is probably 1 to 2 ohms, and going from that 22 gauge to 20 gauge, I mean, maybe we lost like 0.2 ohms of resistance. So in other words, if you were going from like 30 gauge and it was like 40 ohms to 26 gauge and it's 30 ohms or 20 ohms or something, you see a big difference. But here it might be where you're getting to the point where the resistance across the switch is the dominating factor. But let's just see what it does. Now, what I did here is I just set it up to decrement the on time by 5 each time. So it's we'll start at 370 and then just work down, because I can't remember what I measured the induction there. So I'm just trying to find negative 7.9. My gosh, the tension. Isn't it exciting? 8.3. I got a bad feeling about this one. 8.3. We were at 9.13 before. 8.4. Looks like I'm not gonna hit the jackpot. 8.43. It looks like it stinks. I have no idea why. 8.45. There are no splices in the wire. Ugh. Blech. Ha ha! You know what was wrong? These wires are so thick they're not making it through to the breadboard. That was adding resistance. We're at 8.9 and climbing. See, I'm not crazy. Oh no, it's still getting worse. Shoot. 9.09, 9.13 is the number to beat. Shit. Come on. I thought I saw a 1.5. Now it's going back down. Yeah. There was a 1.6. Now, granted, the thing's not stable. I mean, the on time keeps going down. So now we're getting to the point where it's going to be getting worse. Okay, just to show you that gibberish I was spouting before isn't complete hooey. So now, I mean, looked about like 335 was a good timing in terms of microseconds. And 9.13 was what we were getting before. Now it's, oh, come on. It has to be able to read it too. 9.33 there. So, I mean, that's a big enough difference. 9.17, 9.13 was about the best we saw before. Now, granted, it's drifted up from 10 to 10.02, but pretty significant difference. And the other thing that goes to show you is, you know, just if you don't have clean connections, if this isn't in all the way, if these aren't in all the way, it's going to screw everything up. But that's pretty neat, isn't it? You go from 10 all the way back, 93% of the way negative. And, you know, it makes you wonder, how good can that be? I don't know. We're gonna look more at it and look for more ways to improve that. So, all right. Thanks for coming along, and I hope this didn't bore you to tears. And talk more at you later. Ciao for now. Stay healthy. Bye-bye.